Hi, Wes.
Hi, Raymond. How you doing? I unmuted everybody, so it's interesting. Oh, wow, that like unmute everybody. It doesn't just give them control. It makes me listen in on them. I better mute them. Oh, I'm always learning something, I guess. Oh. So welcome to our seminar. I get started here in about one more minute, I guess. But how are things at Ohio State?
It's very well. Well, semester is going on.
Okay, so I'm going to go ahead and get started. So let me let me have you mute yourself just for a second so that I get it broadcast to me. Okay. Anyway, welcome everyone. This is the Nuclear Engineering Department's graduate seminar. I'm Dr. Wes Hines. I'm the Nuclear Engineering Department head here. And today we are very fortunate to have the department head from my alma mater, the Ohio State University. So Dr. Raymond Cao is professor and director of the Nuclear Engineering program at the Ohio State University. He also serves as the director of Ohio State's Nuclear Reactor Laboratory, which is located just off campus or off the main campus. He received his Bachelor of Science degree in Experimental Nuclear Physics from Lanzhou University in 1994, and his PhD from the Nuclear and Radiological Engineering program at the University of Texas at Austin in 2007. Prior to joining Ohio State in 2009, he was a research associate at the Positron Emission Tomography Lab at Harvard Medical School, then at the Center for Neutron Research at NIST, the National Institute of Standards and Technology in Maryland. His major research interests focus on nuclear instrumentation, sensor development, in-pile instrumentation, nuclear radiography, and nuclear analytical technologies. He's published over 100 articles in journals and conference proceedings and serves as the associate editor for IEEE Transactions on Nuclear Science. Welcome, Dr. Cao. Looking forward to your talk.
Thank you very much. Thank you, Dr. Wes Hines, for introduction. It's really my great pleasure and honor to give this online virtual seminar. This has been long arranged even before COVID-19, but now we're in, I guess, a new time. And thanks for everyone actually for calling in, quite a few people. So I'm going to start sharing my screen. I will start to give you a presentation of my recent research on cesium-like tribromide radiation detection. And let me just see how everything works. Okay, I have to use my. All right, before I actually jump into these new materials for radiation detection, I want to give you sort of like a historical perspective of radiation detection and its materials and devices. As you can see here, as early as 1896, there's already X-ray imaging facility set up. In this case, it is in a benchtop environment. There's a tabletop X-ray, and the person here is looking at his hand by a black box. Inside the black box, there's a phosphor to capture light. So this is kind of the one type of radiation detection, which is convert radiation into light. Then you are using a photosensor for detection. In this case, they don't have the sensitive photodiode at that time, but a human eye is actually a very sensitive photodetector. So he's actually looking at his hand by bombarded by X-ray. Unfortunately, there is no protection to his eye, but he's looking at his phosphor emitting lights as the radiation detection demonstration for scintillation. And then there a film detector, of course, being developed. And then in the 60s, silicon detector. And then 1968, kind of milestone is this National Bureau of Standards published the Technical Notes 556 for nuclear instrumentation module. And this is really the milestone for very wide available and being utilized analog system. And then we move on, we have digital systems becoming available. Of course, another big deal is high purity germanium detector in the 70s. That's really fundamentally changed radiation detection in terms of gamma spectroscopy. And now we have CZT become widely available, and digitizer as the replacement of analog system, but both are coexisted and are working in many labs. So it's interesting to look at even today, from 1800s, that X-ray imaging apparatus still being utilized, but with such a great development. And now we have annotated CT scan with machine learning technology. So it's very interesting, but with that perspective, I just want to say, radiation detector materials really have two categories. Either you can use semiconductor materials for direct charge collection, and there are a bunch of these semiconductor materials you can choose from. Or you can use a scintillator to convert radiation into a free charge carrier, then convert them into light. And then light will propagate out of the detector that you can use in photodiode or even CCD camera to capture light. So in this case, we are start looking at a perovskite detector, and it's kind of new materials. So I will say something about a perovskite as also based on a broader picture of what are really required for a good gamma detector. A gamma detector really share lots of good properties of solar cell materials. The silicon, as I mentioned in the 60s, very good radiation detector, but started as a solar cell. The same thing for germanium and the CZT. So it's always, we look at what's been good for solar cell and we can convert that into radiation detection. That is also the case for perovskite. So about 10 years ago, perovskite has really become a very popular, a very well achieved solar cell materials, achieving efficiency, power conversion efficiency about 23%. It takes only several years to accomplish what the silicon has done for decades. But look at how does that being good for radiation detection, we have to look at efficiency, cost, and resolution. If you look at efficiency, it really has to have a large volume. That's the difference of radiation detection versus solar cell. And also look at electron density, right? Because gamma interaction with materials is primarily interacting with electrons. So not only you need to have a high number density of atoms, also the Z number will be larger. That will be good for radiation detector. So, but this kind of like a blue box is what define a materials. Once you have a materials, as the device person, what you can do is look at these yellow boxes where you can actually do this performance evaluation, look at the charge collection efficiency, or you can work on the reduced surface leakage current. That's lots of the fabrication technology that goes in. So that brought up to my major takeaway message from today's presentation is the surface treatment. That is the key to reduce leakage current to improve gamma spectroscopy performance. And also the choices contact metal are very important. So we look at this testing sequence for a radiation detector. As I mentioned, start with solar cells. So you very naturally, you can try laser to look at is there any response, right? Laser producing a very high quantum flux, and so that you can always have some response. The next one would be X-ray. Then you look at an alpha particle, then got a gamma rays. A typical alpha particle is from americium-241, 5.486 MeV. In a typical detector, only produce 0.5 picocoulomb charge. So that's very tiny amount charge. That's why radiation detection is difficult. It's even difficult for gamma ray, which produce 1/10 of the charge, can be produced by alpha particles. That's why you want to try laser, X-ray, then you look at alpha, and both alpha and the gamma ray detection are event by event analysis. They don't have too many common radiation particles come in, so you can actually analyze the pulse one by one. Unlike laser, X-ray, you can actually just look at the current response. So that's why with gamma ray detection, look at it as a typical 662 keV from cesium-137. That's gamma ray, only produced about a 0.05 picocoulomb charge. So that's really tiny amount. That's why we really are talking about a low level signal, and we have to really focus on improving signal to noise ratio in order to get this charge converted into voltage, then do analysis. So I'm gonna actually give you 1 minute a class lecture on radiation detection. I teach radiation detection at Ohio State, 3 credit hours, but here 1 minute you get my free 3 credit hours. We just focused on mu tau E. So what is actually mu tau E? Because I'm gonna talk about all about mu tau E in my talk. All right, so mu tau products, it is the most single important parameter describing performance of semiconductor radiation detector. If you go to a conference talking about a radiation detection, looks like everybody will talking about mu tau E or mu tau for semiconductor device. So what is actually a mu? Well, look at this very simple structure. I just like to use this planar structure for radiation detection. This could be a semiconductor device, or it could be a gas chamber. I forgot to mention in my previous slides, I introduced the detection materials. So actually the most widely available, the lowest cost radiation detection materials is actually the air we breathe every day. So that's what's been used in the millions of smoke detectors for radiation detection. So you can imagine here has the air, high resistivity, often likely case, high resistivity is like a semiconductor device, has this depletion region, has very high resistivity, lots of similarity. So I have radiation coming from site and producing a charged electron hole, electron ions, then gonna travel, driven by the external voltage, and electrical field will travel from this anode to cathode. So look at this definition. So velocity of the carrier velocity is really proportional to the electrical field you're applying, right? So mu is nothing but it's like a parameter define proportionality of the carrier velocity versus electrical field. But it has a very fine units. In order to balance out units, have this mu mobility of whole electron have units of square centimeter per volts per second. Well, the second parameter is lifetime. It's easier to conceive carrier lifetime because you want a carrier to survive long enough before it can travel from one electrode to the other electrode in order to be collected or in order to induce charge in the external circuit. So then you times mu tau together. It has another funny unit is square centimeter per volt. So I guarantee most of people will have no idea what is mu tau by looking at these products, by looking at this as units. So let's do a little bit of magic here. Now, if you look at a tau over t, where tau is the carrier lifetime, t is the time it takes for carrier to travel or drift from one electrode to another electrode. Right? You always want is tau lifetime longer than the t travels by this charge so that it can be collected. So it's really the competition of this lifetime of the carrier versus how long it takes them to travel. So if we actually times velocity on the numerator and the denominator, then you see the magic. Then we have this because V is defined by mu E. So now you have mu tau E. And the Vt, of course, is the distance. That is the thickness of the detector the charge will travel. So now this makes a lot of sense because the units become a centimeter. So mu tau E has the unit centimeter, and mu tau E is also the computation of, we call that mean free, free carriers mean free path. Free carriers mean free path, or carriers mean free path. So this mu tau E is the competition with detector thickness. If mu tau is larger than detector thickness, you will get 100% charge collection. So radiation detection is really just all about, well, for semiconductor device, all about this competition of the carrier mean-free path versus detector thickness. Well, because this detector, because the electrical field is the external parameter user control. You want to apply high voltage, you want to slice your detector, make it thinner. So there's not quite a materials property. So that's why people now starting to talk about mu tau as the most important parameter describing a performance of radiation detector. Help you, get a little bit on better understanding what does mu tau mean. I have to put in the perspective how does charge travel to induce charge, and put into perspective this mu tau E. But anyhow, now we're gonna move on to this inorganic cesium-like tribromide detector. Has wide band gap. It's good for room temperature operation. Has high Z and high density for gamma ray sensitivity. Has large carrier mobility lifetime, which is mu tau E. That's good for detector performance. And well, other good about this detector, detector materials is low cost. So Dr. Makari Kanatis' group at a Northwestern group actually has done a fantastic job. They grow this cesium-like tribromide by melt methods, high temperature melting. They can go large crystal, and they have achieved 3.8% resolution at a 662 kV. So what I think they also achieved 1.4%, because I saw their presentation last year in IEEE meeting at Manchester, but I haven't seen it in the paper. But 3.8% is a very, very good performance compared to other detector takes many, many years to achieve. So, but what we're going to talk today was different with Dr. Kanasidis' research is we're not going male girls. The detector here is provided by Dr. Jinsong Huang's group at the University of North Carolina and the Chapel Hill by Solution Girl. So Solution Girl can give you a much lower cost of materials. And now we're trying to produce a device have a good gamma spectroscopy performance. So now this, we look at this few relevant materials. Now I think you have a better idea of what mu tau means. And of course, mu tau should be larger, right? Larger the better, because if mu tau larger, mu tau E will be large. And mu tau E has the units of centimeter. You want mu tau E longer than detector thickness. Remember that, right? So the mu tau should be larger. So look at the cesium-like tribromide versus this is another version of perovskite, methyl ammonium, like bromide as inorganic organic hybrid. Has also pretty good performance. But the problem with this hybrid, the halide, is that they have not very stable in the environment. And also compared to CZT, we can see what's the gap between cesium-like tribromide compared to CZT. But there's lots of progress going on with cesium-like tribromide research. Particularly the cost is relatively lower compared to CZT. I'll give you a little better idea of the cost of this cesium-like tribromide. And its Solution Girl, as I mentioned, is different with Northwestern group. They're doing melting girls, and we're doing Solution Girl by University of North Carolina. And here's the recipe, was already published in this paper. The materials really purchased just off the shelf from Sigma Aldrich. We're not even using this, the top one has a 5.9 purity. We're really using the lower one, has pretty high concentration impurity, I would say. So that's one of the property claimed by perovskite has pretty tolerance to impurity level in the solution when it's grow. So before I going on to talk about to get results of our research, I just want to touch base on the instrumentation. And this is the very typical analog-based instrumentation for radiation detection and signal processing. You have the chart, radiation producing charge, producing current convert into a voltage, then you process this voltage, right? So this is a very traditional way of doing it. It is the typical gamma energy histogram or gamma energy spectrum. Actually, I acquired when I was at NIST, a study dust that coming back from moon. So we did a neutron activation analysis to look at so many gamma lines. So the goal, why do we, actually here is a good example to show you why do we want a good resolution? Because if you have a good resolution, these peaks will be very narrow so that you can actually tell what isotope in the materials. If this peak are broadened, you will not be able to separate these peaks to identify elements or isotopes in the samples. So that's why example will show why do we want this. We look at energy resolution, we want it as small as possible. And then since 2000s, people has a lot of labs, what I can see is have started using a digitizer-based signal processing, for which we have also started. And you can get this digitized waveform. And in our analysis, we actually did we applied a timing filter, trapezoid filter, timing filter getting time signal, time information, trapezoid filter get energy information. And this is one example of boron carbide in neutron beam irradiation. We can reconstruct the spectrum based on this mode data. So it's all can be done by algorithm. But if digitizer, they have already written firmware into this digitizer, so you have not much of freedom to do it by yourself. But in other cases, you can actually write your own digital post-processing algorithm to try to process this spectrum. So what's the next? Well, maybe you can try AI. I don't know, this is one example. This company has tried, and there are lots of the research going on in this area. It's very exciting. We see what's the next lead to this instrumentation for radiation detection. So what has been used for this research? We actually applied all of them. We tried an analog system, we used the digitizer. We also have this ourselves developed digital post-processing and to process the signal from oscilloscope, which is the full capture of waveform data. And we capture that and we can actually save into spreadsheet or use in MATLAB. You can run this data analysis. Really to get rid of all this analog system except for the ADC part. So now look at what's the response of cesium nitride response to alpha particle. So as I mentioned, alpha particle is coming from a lithium-241 source that is widely available in smoke detector. Over the smoke detector, if you look at your roof, you probably see one. They have 1 microcurie lithium-241 in there, and they emit 5.468 MeV alpha particle. So in this case, we shine this alpha particle from the titanium side of the perovskite device. There is 2 centimeter air, so the peak will be broadened. So it's very key to see that we are able to acquire this alpha spectrum also with the increasing of voltage. And you have more charge being collected. And so we have this the photo peak, I mean, this energy peak will shifting to the right. So that just showing you have a clear spectrum acquired with increasing voltage if you shine the alpha particle from top, right? If alpha particle shooting from the top, their range is pretty small in these materials. Cesium nitride bromide is only less than 20 microns. So the charge is pretty much produced from the surface. So you're actually driving holes down to collect it, just ignore the electrons, because charge is being produced by the induced charge. So it's interesting now, if let's do a switch. So nothing different of this one than this one, but we switched the source to the bottom. So now we shine from the bottom, which means we're producing the electron hole pairs at a very near surface region where electron gonna be driven by the electrical field, and the hole will not be contributing much to the radiation to the detector signal. So this is clearly indication in this case that a spectrum looks pretty bad. So which means this whole transport in perovskite does not produce a good energy spectrum. There are lots of trapping going on for electron transportation in perovskite. This is different than CZT. Well, if you are in this area, you probably know CZT has pretty good semiconductor, room temperature semiconductor detector, but has a problem with the planar structure. You will see this whole tailing effects. The tailing is defined as a symmetric photo peak with the tail towards lower amplitude. So that is contributed by the hole because hole travels slow, right? Remember it's mu tau. When mu tau is small, so mu tau A is smaller than the detected distance, and also they travel slow, and they will not be completely 100% captured. So they will actually have some lost charge collection. Well, compared to CDT, we can see from this example, showing the hole dominate charge transport versus in this picture, electron dominate transport, that is clear to see, and a perovskite, the spectrum introduced by electron is much worse than that of a hole. So we're gonna see electron tailing. Okay, if we look at a single pulse coming from perovskite, and in this case is the hole induced signal. Look at this, has the rising time is 60 microseconds, very long. All right, so there's also another problem. In this case, we're assuming the charge drifting time. Remember the coplanar structure, the charge will drift. So the time take charge to drift, you can see that by looking at the pulse rest time. So this pulse rest time is kind of equal to the charge drift in through the entire volume of the detector. So it takes 60 microseconds for charge for hole to transport. That's very long. So with this very long, we have something called ballistic deficit. That is when charge transient time is larger than RC constant of the circuit. So you just don't have enough time to charge up your capacitance in the other circuit, so that you're gonna lose amplitude. So for this reason, we do not have a mu tau evaluated by Hatch equation. Hatch equation is not applied because the amplitude of the pulse, each pulse at different voltage is not fully reached to saturation. Well, instead, what we can do is, and we can look at just look at a histogram of this many thousands of poles, their rising time. So in this case, you can see the rising time has a function with the applied voltage, right? External voltage, as I mentioned earlier, and you can apply higher voltage, and because voltage equal to mu, the velocity of the carrier equal to mu mobility times the electrical field. The higher the voltage you apply, the velocity will be, the carrier will be faster, so that you actually can see them for 450 volts is about 60 microseconds, 500 volts about a little bit over microseconds, a little bit over 50 microseconds. So from this one, we actually can make a plot of electrical field versus whole drift velocity, right? So why we want to do that? Well, it's because the drift velocity against the definition equal to mu E, and electrical field equal to voltage divided by distance or thickness of the device. And also velocity of the carrier equal to D divided by T, which is also the thickness of the device divided by T times, the T is the transient time, but now we're using preamp signal rising time to substitute for this transient time. So if we make these two equal to each other, we actually can figure out what is mu. So this is also, you can call that time of flight methods. So the mobility is really just constant by fitting these lines of the whole drift velocity can calculate by this equation, and the electrical field what you have applied. So that we figure out for whole mobility is 1.78 square centimeter per volt seconds. So now let's switch the gear, look at our detector fabrication. We did polishing, surface passivation, pixelation, and also look at the different architecture of the device. For radiation detection, what you can do is, well, you always want to have a materials with very high resistivity, right? That's why air is good, because it has high resistivity. And you put the 2 electrodes, that's a radiation detector. A diamond is good as well, because diamond has also very high resistivity. If a semiconductor, you have to do some doping to make sure you have forming some depletion region. So for a good material with high resistivity, you can always apply ohmic contacts on the both ends. Put a metal there, you're gonna have this symmetrical double ohmic structure, that's it. But the bad about this double ohmic, the simple structure is, the higher the electrical field you apply, the higher leakage current. So it's not very good with high voltage application, but which is needed for gamma detection. We always need to apply very high voltage to increase the drifting velocity of the carrier. But for what's other option? So the other option is for cesium like tribromide, which is PTAP, we can either apply a low work function metal, that will form a Schottky contact, or you can apply high work function metal that will form ohmic contacts. By doing so, you have 2 options. You can form Schottky ohmic structure or double Schottky structure. So that's where we have done for our device structure. Basically, we applied this either low work function metal or high work function metal to form double Schottky or Schottky ohmic structure. That's where I'm going to show you lots of devices, their performance based on this structure. So for the polishing, and what we did is we applied a diamond paste and tried to polish surface. We did cleaning by tutoring. There are also surface oxidation, but I have to admit that we're not purposely to do surface oxidation or passivation. Is really unintentionally oxidation that form oxidation layer that helps to suppress the surface decay current. And here's at one state of research, we were using zirconium as the electrode. We put a gold on the top of the zirconium as the protection layer. So that's zirconium, cesium tribromide zirconium. So zirconium is a low work function metal. So this will be forming a double Schottky structure. What I'm showing here is double Schottky structure. It's kind of like linear, but if you zoom in the middle near a 0 region, it will say the double the blocking effects. But we also have applied this the gold protection on the pixelated detector. Some of them does not cover very well. So that's why actually some of them doesn't really show this double Schottky structure. Showing this Schottky ohmic structure, we guess that's perhaps because the gold is actually contact the materials. You actually on one side you have this zirconium, other side you have this a gold contact. So the surface passivation, as I mentioned, we did not do a purposely passivation by oxidation layer, but we suspect there native oxide formed during fabrication. And this is confirmed by SEM picture. So this SEM picture on the bottom is really just cesium, bromide, and lead and elements, but on the C picture is showing is the oxygen. So that's kind of showing their uniformly formed oxygen on the surface. So with all these improvements, the device structure, we did a double Schottky or Schottky ohmic structure, and after polishing, pixelation, here is the kind of the leakage current we have achieved. Well, the first chromium, we've been studying chromium for a long time, but it turned out chromium is not the best. And the leakage current is pretty high, over 100 nanoamp at 30 volts. That's why it's ruled out, because this high leakage current also is kind of have high reactivity with the with perovskite. So we tried a gallium gold, and that shows a pretty low leakage current. At 100 volts, this one shows 8 nanoamp, and the 200 volts, this one shows 2.5 nanoamp. So with that improvements for the device structure and their surface, we will start to look at their gamma ray performance. gamma energy spectrum performance. And this is the gamma spectrum acquired for cesium-137, which is this one, and cobalt-57, emitting primarily 122 keV gamma rays, and also americium-241. Well, wait a minute, I just mentioned americium-241 is the alpha source, but americium-241 also emitting a gamma ray at a 59.5 keV. Has about a 23% yield from one alpha particle emission. So that is actually gamma ray. It's not an X-ray. It's coming from a transition of energy level of the daughter nucleus. So we using this americium-241, use that as a low energy gamma ray source, and also produce pretty good spectrum by cesium like bromide. And we also compare with CZT. In this case, we purposely bought a smaller CZT detector, 4 times 5 times 5 a cubic millimeter, that has pretty close dimension as the perovskite we're testing. We just want to say, you know, as a benchmarking, the device volume would be similar, and to see what the performance of their response to radiation. And so here is another case. I did a switching of a alpha source from top and the bottom. This is case with switching gamma source from top and the bottom, because gamma source also will be producing electron hole pairs. If gamma source has low energy, and that will produce some near surface charge. In this case, we tried americium-241, 59 keV. Now we put this gamma source to the bottom. We look at how does electron transport produce a spectrum, and in this case is how does electron transport produce a spectrum. As again, this is already been demonstrated by alpha particle. Just like I mentioned at the beginning, after you're done with alpha particle, it's much easier to work to get a signal, and you want to switch to a gamma source. So in order to get a gamma source, you got just a real case demonstration. How does this carrier transport affecting gamma spectrum? It shows like it doesn't really, it does make a lot of difference. The whole induced spectrum is much better than electron induced spectrum, right? This is for 59.9, the gamma ray from americium-241. Let's look at it for cobalt-57. Cobalt-57 energy is higher, so it's going to penetrate a little bit deeper into materials. So the difference of electron and hole causing the spectrum will be not as significant as what the americium-241 does. So that you can, in this case, we say the electron will producing a smaller peak here, but of course, much worse than what the cobalt-57 being produced, has been able to produce a peak. But if you look at a cesium-137 has 662 keV, that will just penetrate entirely of this small detector, right? In this case, it doesn't matter where you place the source, and the electron hole pair will be produced uniformly in the device volume, so that the signal is actually producing coming from the averaging of hole and the electron transport. So as expected, you will not see difference. Well, there might be some difference, but look at this spectrum, we really don't see much difference of these two spectrums by switching the position of the source. I think this is a very good illustration in a real case, because you can try X-ray, you can try alpha particle using laser to get a spectrum or signal response, but with a real gamma source, what is shown here is another verification of the whole dominant transport of perovskite for signal production. We also did a Gen4 simulation. We want to say was the size affecting the spectrum. Of course, the size matter, and for smaller device, you will not have a good Peak-to-Compton value, but for a large device, you will have a much better or much higher Peak-to-Compton ratio. So this is another demonstration. We look at the three spectrum by americium-241, cobalt-57, and cesium-137. Look at the energy linearity. And as shown here, they're quite linear at a different energy, this perovskite for radiation detection. So now we're moving on. As mentioned, we look at a lot of zirconium, and but zirconium has some problem. There kind of like a lot of cracking formed. It's not very stable. Cracking formed right after metal deposition also is not very stable after a few weeks, and they were just forming cracks if there were not cracks formed at the beginning. So we look at a few other options. Look at bismuth, titanium, gallium. Gallium is always good, has a pretty melting property, but it's room temperature melting metal. It's not good for the field application. Bismuth has a very small melting point, so that does not induce much thermal stress when you actually do metal deposition. So theoretically, it should be working better. So this all has been tried and approved, and their performance. So I'm showing you here is these four metals actually. Zirconium structure, that is double shocky. Bismuth, this is double shocky. And what's shown here, right? These two are, these two are double shocky structures, zirconium, bismuth. They're kind of linear, asymmetric. Asymmetric would be the shock only structure. That is titanium, gold, or gallium, gold. We'll also look at a platinum CZT as a comparison. What is really good about this demonstration is look at its leakage current. At 200 volts, the leakage current only a single digits or 2 to 3 nanoamp. So that's a very good sign. We will get a pretty good gamma spectrum performance. So here's the gamma energy spectrum of different metal forming different architecture. And they all showed up a cesium 137 gamma peak. And what I want to emphasize is this one. I really like this titanium cesium like tribromide gold structure. They're showing a peak very clearly visible with Compton, with the peak-to-Compton value ratio of 2. Well, the reason this one has a better the spectrum shape is because this one is actually planar structure, so that you have, compared to other three, they have on one hand, on one side is planar, another side is the pixelated. So when you have a pixelated, the effective detector volume will be small. So that's also verified by our Gen 4 simulation for planar structure, because the effective detector volume is large, then you will have a better spectrum shape. The resolution would not be necessarily will be the best, but it definitely will have a better Compton, peak-to-Compton ratio. Well, I'm gonna move a little bit faster about the digital post-processing. I just want to show that we have done this. Don't want to emphasize what we have, focus on what we have done. Just want to show that we did process the digital post-processing and to process this spectrum. Well, this is actually to show the detector with a faster transit time at the most probable 4 microseconds, which is good because you typically need a 10 microseconds for that's kind of like a rule of thumb. If the transit time larger than 10 microseconds or 10 microseconds, you will have a ballistic deficit. But if you less, you could have a pretty good physical reconstruction of the spectrum. So this is the example of good detector with 4 microseconds transit time. This example of bad detector with 20 microseconds transit time. So what we're showing here is we didn't do this analog analysis. We just got a waveform from this oscilloscope, and we just applied a DPP algorithm to it. And here is the demonstration, a validation of DPP by commercial silicon CZT with analog system. And you can see they're quite a great of our algorithm compared to analog system. Here's the case to show that DPP can applied, try to improve. On the left is the one is a good transit time, small 5.8 microseconds, less than 10 microseconds, so that when you're using an analog system or DPP, you get a similar spectrum shape. But for this 20 microseconds, there will be ballistic deficit, you're gonna lose the peak information. So we apply the DPP, we actually can restore the peak information. So that's what I'm trying to say by this slide. All right, lastly, we'll look at cesium like tribromide detector stability and reproducibility. And one case we applied, the detector applied voltage bars and no, wait, well, sorry. So in this case, we just look at their leakage current on a consistent time scale. And this one for 5 hours. And this bismuth cesium like bromide gold structure, their leakage current maintain a pretty stable level and also very small. And the other one we did more than 1 hour is also quite stable. The figure on the right is trying to show this device for gamma ray spectrum. We did the 20 hours counting. We're not accumulating for 24 hours. We acquire one spectrum at the beginning of the 24 hours, and then another one at the end of 24 hours. We just want to see are there any shift of the spectrum. This one does not have a pretty good peak visible, but the entire spectrum does not change at all over this 24 hours period of time, which means device is quite stable. Here is showing you we not just have one device, we really have fabricated a lot of devices and try to look at their IV curve. It is pretty consistent for gallium gold structure in this case. There's 3 different devices fabricated at different time, and they all show very low leakage current at 200 volts bars. We also look at iodine doped cesium like tribromide versus chlorine doped cesium like tribromide, but iodine works better in terms of leakage current, and this is not acceptable. 100 nanoamp is too large. But again, none of them actually produced a meaningful spectrum. So we eventually will still focus on cesium like tribromide, not doing this, the doping, try to compensate carrier trying to produce high resistivity materials. Well, lastly, we also look at a neutron response. And in this case, it's not cesium like tribromide, it's not organic perovskite, it is the hybrid perovskite. Has methyl ammonium like bromide, and also has chlorine as doping. So because they're hydrogen in the semiconductor materials, very natural, intuitively can think that a neutron coming, a particular fast neutron, the hydrogen will have recoil, that recoil hydrogen becoming a charged particle. So this is really just charged particle detection. At Ohio State, we have a reactor, 500 kilowatts, we have a thermal neutron beam. So it's very easy for us to place the device in the thermal neutron beam. And in this case, we try to block thermal neutron beam by lithium glass to filter thermal neutrons. So with the residual fast neutron, we want to see what's the response, because this is really for fast neutron detection, because hydrogen recoil. It's not for thermal neutron. And looks like there are clearly signal response after device being placed in the neutron beam, after thermal neutron is being blocked, and there's pretty good. We haven't got a chance to publish this data, but I just want to show you here. So my conclusion are 2 minutes, over 45 minutes. So my conclusion is the leakage current in this case has been consistently achieved at about 2 to 5 nanoamp at 200 volts bars. That's really comparable to a commercial CZT detector. So we developed the surface treatment, polishing, and device fabrication for pixelated detector technologies. And we tested the reproducibility and the stability of the device. And we conclude that gallium is good for lab testing, but bismuth and titanium, they are all pretty good for field application. The best achieved resolution is in the range of 5.5 to 11%. And of course, the best is 5%. And it's not as good as the group at the Northwestern University, but the difference of our research is based on really low cost materials, and because the solution grows perovskite. All right, I want to thank the sponsor, Defense Stress Reduction Agency, and also many students, postdocs have been working on this projects for years. The Dr. Huang's group has sending us under the supply of devices materials. We really, like I mentioned here, we damaged, destroyed, and lost a lot of them. I really appreciate this collaboration with Dr. Huang's group. All right, thank you very much for your attention. Don't know if everyone is still with me. All right, I'm going to stop sharing. Okay, we'll see any questions.
Okay, thank you. Yeah, we have 91 people still attending, so we haven't lost everyone.
That's good.
Yeah, do we have any questions? I have to make sure that I give people an opportunity to unmute. So if you have any questions, go ahead and unmute or raise your hand or.
Hi,
Okay.
nice talk.
Thank you.
I was just wondering, you mentioned surface passivation at one point. You think that you sort of incidentally formed some surface oxide layer. And surface passivation has been a very hot topic in perovskite solar cells.
Right.
Have you tried any intentional passivation approaches with your detectors, or do you have any intuition for how much difference it may make in the detector performance?
Yeah, it's a good question. We actually tried in the past, but not for this device, for a hybrid perovskite with Dr. Huang's group, and also that's collaboration with, I believe, another group, a professor, another university, I don't quite remember. So in that case, we did O3 passivation and trying to improve the surface leakage current, reduce the surface leakage current. Has a huge impact. So that device was designed for X-ray imaging. There's a paper published talking about how does the performance being improved in terms of X-ray imaging. And for this one, we did not apply any intensive passivation process, really just oxidation naturally formed with zinc, just verified by this as EM. And we think that really helps to improve the device performance.
So one thing I'll mention is I worked on a project using urea hydrogen peroxide as a gas phase passivation to accelerate the oxidation that you see at the surface.
Yeah.
And we could increase the steady state PL signal by an order of magnitude with that for perovskite thin films. So it might be something that you want to try if the surface oxide has a big effect.
Yeah, absolutely. I'm very interested. Yeah, I would be very interested to have this collaboration. Actually, to try some passivation process to say how does that affect performance of the device. So far, it's 2 to 3 nano amp at 200 volts is pretty good, but I think we still have a lot of issue with the bulk leakage current or the defects in the bulk. So that's another potential improvements can be done.
Okay, and I guess the last just quick thing I'll mention is that there's a lot of work now on 2D surface treatments with organic chains, which may help improve your resistivity at the contacts as well. In addition to providing some surface passivation effects. Anyway, we can talk more later. I think we're on a
thank you.
tomorrow,
Thank you for the comments. Yeah.
Kelly, do you want to introduce yourself and tell us where you're from?
Sure. Yeah, I'm a postdoc at the National Renewable Energy Lab. So I'm just getting into the radiation detection field. I come from a PV background. I was in Henry Snaith's group for my PhD, where I worked on perovskite solar cells. And I'll be at NREL at least for the next 3 years working on perovskite radiation detectors.
Great, thank you.
Thank you for the comments.
Dr. Lacosi, do you have a comment or question?
Yeah, I'm interested because we polish our we do chemical mechanical polishing on ours to remove the damage from the lapping pads. Do you think you're having any effect of surface damage on the surface recombination velocity?
We don't know actually exactly what's the surface damage caused by polishing. The polishing does remove a thin layer of the materials. So for the device actually are tested for all these different metals performance, they are actually the same crystal. We keep polishing the same crystal, which means we deposit the metal and wash it out, and we deposit, the polishing, cleaning, then we deposit metal to make a device. We want to say want to reduce the possibility of the crystal to crystal quality variance to the detector's performance. But after every polishing and washing, there are layers of materials being removed. And for us, it's really look at it's good or bad. It's really just by looking at a IV curve after metal deposition. So we did not actually to look into any other surface properties.
Yeah, I mean, we haven't played with this all cesium version of this material. You know, we're still trying to figure out how to grow it to this volume. So we're still using the hybrids, and you may be familiar with the, well, actually, no, it's still under review. But it was at the IEEE conference where the DMF polishing, chemo-mechanical polishing at the end increased its stability by like a factor of 4, so you could put 4 times the bias on it.
Mm-hmm.
But yeah. I have another question. I'm sorry.
Well, just comments. You raised a good question about the surface polishing for hybrid perovskite. We worked on that for a few years, and the problem, yes, we did a polish as well, but the problem is it's sensitive to environment, and it better, so which means after your surface process, it's better to encapsulate as soon as possible. So we have tried to using a epoxy to just to block everything, to seal everything. People have used wax to seal the device right after your polishing to maintain the surface structure. Otherwise, you're probably going to react with moisture in the air. But the problem is also with encapsulation with wax or the epoxy, it will cause the thermal stress to the materials, because this material is also pretty good at piezoelectric materials. And then it's just really hard to control the performance. I know what you're talking. I mean, we also spend a lot of time trying to figure out how to do that.
Yeah. So when you said that 100 nanoamp current was too high, I'm just curious why, because several large area silicon alpha detectors pull more current than that, and they have very good energy resolution.
Yeah, right. So you're probably talking about one I mentioned. I think this one kind of make a comment is 110 nanoamp is too high. Well, if we just look at a surface leaking current compared to other, this is kind of high, and we have not able to produce gamma spectrum. So we kind of attributing the reason we get a gamma spectrum is because surface leaking current. But well, by saying that also, we're kind of just saying we gave up on the bulk property. Because the bulk property, bulk leaking current, or the trapping is really just the materials being provided to us, and Dr. Huang's group, they're producing a pretty good high quality materials. Because once we have that materials, the only thing we can work on is the surface. So that's really I meant from this perspective, and we only look compared to the surface property. We will say this 110 nanoamp is not good enough. But in the case you mentioning, their materials, if they have a pretty good bulk property and low leaking current in the bulk, and even the surface leaking current is high, and there should maybe still be able to work out.
Yeah. I mean, lower current is definitely better, and I guess I missed that it said it was at 30 volts. So that's part of the problem.
Oh yeah, right. Yeah,
yeah.
Right. 30 volts. Yeah, right. It can go to 100 volts. 200 volts, that would be very high leaking current.
Yeah, well, I just wanted to say I appreciate you coming and giving the presentation. I wish my invitation could have been, for you to actually be here, but, I appreciate
Don't worry,
it.
I'll go there again.
Yeah.
I'll go find you.
All right.
Great, Dewey. Do we have any last minute questions? Okay, so again, thank you, Dr. Cao. It's always a pleasure to see you. I enjoyed my visit. I guess it was last year up at Ohio State. Always nice to go. I was born there at Riverside, so always appreciate that. And I appreciate in your slides having all those orange pieces of material. Since orange is our color, I appreciated you taking care of us today. So have a great day. Take care.
All right, you too. Have a good day. Bye, Eric. Thank you.
Yep.
Thanks, Lance. Bye.